Welcome to lecture 24. In this lecture, I will be talking about killing vectors. Recall that we've discussed the Noether theorem and conserved charges in Minkowski space in lecture 8. In this lecture, we want to consider an equivalent of this Noether theorem in curved manifolds. The corresponding conserved quantities are called killing vectors, and these are the subject of the present lecture. Specifically, in this lecture, I will summarize or derive the killing vectors from the geodetic equation, and we will be talking about examples of killing vectors also in this lecture. Let's start with the derivation. So the geodetic equation is given in equation 24.1, and we have seen this equation many times before. What I want to do now is that I want to rewrite the geodesic equation for downstairs indices. So instead of having a mu upstairs, I want to pull it down with a metric contraction, and similarly, I want to act on the Christoffel symbol in such a way. So we find the equation, the geodesic equation with downstairs indices given by equation 24.2. Now I want to denote these coordinate derivative with respect to proper time as velocities. So I'll introduce the notation u being equal to the derivative of x with respect to proper time. And then this equation here, equation 24.2, can be written in much more compact form. So we get d u mu downstairs with respect to d tau is given by the Christoffels acting on u alpha, u beta. The Christoffel symbols are, of course, given in terms of the derivatives of the metric tensor. If you plug in the definition of the Christoffel symbols in the equation that we've just written down, we find a lot of derivatives of the metric tensor. And for notational brevity, I will denote these derivatives of the metric tensor by a simple comma. So whenever you see some object and a comma with an index in the index position, that denotes derivation with respect to the coordinate mu. This is a standard notation in general relativity, and I will be using this from time to time throughout the rest of the lecture. Okay, so if we now plug in the definition of the Christoffel symbols in the geodesic equation written in terms of this variable u, this is what we get. So we have 1/2 metric tensor and 3 derivatives of the metric tensor that's coming from the Christoffel symbol. Now, if I take the metric tensor and act on the u with a downstairs alpha, this just gives me a u with an upstairs nu. And the combination u nu, u beta is, of course, symmetric in the indices nu and mu. So if I change nu and mu, there's no change in this product. This is important because if you look at these two terms inside the parentheses, let me sort of focus on those, you find that these two terms are actually antisymmetric in nu and mu. So if you change antisymmetric in nu and beta. If you change nu and beta, you get beta and nu, so this is this term here, but we have a minus sign in between. So if we change nu and beta, we get minus nu and beta. If we change nu and beta in this product here, we get the same. A symmetric times an antisymmetric product always annihilates to 0. So basically these two terms just drop out, and the only term that we have left that does not drop out is this first term in the equation here. So our geodesic equation simplifies considerably, and we get the following form of the geodesic equation in downstairs coordinates. The u mu downstairs is given as 1/2 g nu beta derivative with respect to mu times u nu u beta. So let us now assume that we have the following situation, that our metric tensor, or the metric tensor component nu beta, is independent from a specific coordinate. The coordinate x mu, and this can be time, it can be the x coordinate, it can be some radial coordinate. For the moment, it does not matter which coordinate it is, but if we have such an independence, clearly the derivative of the metric tensor with respect to this coordinate must vanish. If this is the case, then this term here is 0, and our geodesic equation simply becomes du mu by d tau is equal to 0. From this independence of these coordinates, it does follow that since the derivative of the velocity with downstairs index is equal to 0, the velocity with downstairs index itself must be a constant with respect to proper time. So what we find is that if we have independence with respect to one coordinate, we have some sort of symmetry, if you want to, and this symmetry creates a conservation law where a specific quantity, in this case this u mu, is constant as a function of this coordinate. So there's something like a conservation law, and because of this, we have something that is in many regards similar to the Noether theorem that we derived from Minkowski space. Let us do an example of this. Let's be concrete and assume that the coordinate with which the metric tensor is invariant to is time, t. So then the derivative of the metric tensor with respect to t is just vanishing. So the operator dt acts like a symmetry. Of course, we may write the operator d by dt or partial t as a Kronecker delta mu t acting on the 4 gradient partial mu. If we do this, then we can write this formally as a contraction of 2 4 vectors, one the 4 gradient and another vector k mu, where k mu we call the killing vector. So in our case, the killing vector for this example is simply given by delta mu t. So it is, if you want to, yeah, it is some sort of matrix representation that has a 1 only in the 0, 0 component and has 0 everywhere else. If we have identified a killing vector, then the conservation law is simply given by the contraction of the killing vector with respect to another vector of the system. In our case, it's the 4 velocity u. So we have k sigma u sigma is equal constant. That's the conservation law that follows if we have a killing vector. And of course, for the killing vector that we have in our example here, delta mu t, if we plug this in, we find that this constant is equal to delta sigma u sigma t. And we can make the contraction and find that ut is the quantity that's constant as a function of time. Of course, this matches our derivation that came directly from the geodesic equation if we take the coordinate mu is equal to t. The physical interpretation of this is, if you want to, kind of trivial. It just says that if the metric tensor itself, G, does not depend on time, nothing depends on time, and hence the Lorentz vector is time independent. You would say that, okay, this is maybe a trivial example, and I would agree with you, but the point is that we can use killing vectors in more complicated situations. So for the example that I've given, it's hard to see why one would use killing vectors in this particular example, and indeed I would agree with this. However, we will discuss more complicated examples, in particular more complicated coordinates, where spotting killing vectors and knowing how to use them becomes useful. And the example where this becomes useful will be revealed in the next lecture, when we will be discussing killing vectors in the Schwarzschild geometry. So this ends the present lecture.